how was the midterm? I mean, fair, not fair? I thought it was pretty fair. We worked hard on that. We pre-tested it. I always judge a midterm both by how well it tests the material, but also by how many clarification questions have to be corrected during the midterm itself. At least we scored good on the second measure. So we hope to have that graded by the end of the week, and we'll announce on Piazza how to get that back to you. Okay, so back to content. Today we're going to talk a little bit more about EM, which has to do with how we train machine learning systems, especially BayesNet-oriented machine learning systems, when we don't really have fully observed data, when some of the variables of some of the training examples are missing. So we'll talk a little bit about that. And then we're going to talk about how this actually gives us an algorithm for totally unsupervised clustering. So it turns out clustering sounds like a different problem than we've been working on, but it turns out we don't need a new algorithm to do clustering. EM is a perfectly acceptable, one perfectly acceptable algorithm for doing clustering. So we'll look at that. And then we'll look at, remember when we were talking about training Bayes nets, we mentioned that there are different, sort of 4 different versions of that problem, depending on whether the structure of the Bayes net is given in advance or not, and also whether the variables are fully observed or not. And so I guess so far we've looked at the case where the structure is given and the variables are fully observed or not. That's EM. But we'll also look today at the worst case, the fourth quadrant of that, where neither the structure, well, I guess we'll look at where the structure is not given, but the data is observed. And then you can extrapolate from there how to get to the evil fourth quadrant. We'll talk a little bit about that. So that's the plan for today. So I want to begin by just, again, reviewing EM. So EM is an algorithm, we think of it as applying to Bayes nets. Remember we had this Bayes net we were thinking about before where we had variables like, do you have the flu? Do you have an allergy? Do you have a nasal problem of some kind? And do you have a headache? And are you sneezing? So a simple little medical Bayes net. And when we talked about EM, we looked at the example where some of those are observed, 4 of those are observed. I'll color in the ones that are observed here. And one of them, N, is not observed. And then we brought up EM as a way of training in general Bayes nets when only some of the values of some of the training examples are observed. And we said that informally the idea is we go through the EM process where informally the idea is that on the E step we will estimate the values, we'll get the probability distribution over the values of those unobserved things like N. And then on the M step we'll use those inferred values of the unobserved variables to estimate the parameters of our Bayes net. And we'll iterate that process. And as we mentioned, this is guaranteed to lead to at least a local maximum in the expected log likelihood of the full data. And here I'm using X to refer to the set of observed variables, and Z the set of unobserved variables. So this is kind of nice that we have this guarantee that we'll be able to get parameter estimates and also assigned values to those unobserved variables that correspond to a maximum, we like to say maximum likelihood of the full data, but since we don't really observe the Z's, we have to say it's the expected likelihood. Okay? So then a little bit more precisely, the E step, as I mentioned, is to use the observed data X and the current parameter estimates to calculate the probability distribution over the unobserved variable Z. And then on the M step, to choose a new theta based on the old theta that we already have. To choose a new theta based on the old theta that we already have by finding the theta prime that maximizes this Q function, which is just that expected data likelihood. And we went through an example here where, assuming that the sinus variable is not observed, well, we went through an example where on the E step, we noted that using our standard rules for Bayes net inference, we could estimate the value of the S variable given the other observed values on the kth training example. And that was simply this expression, which, by the way, should look very familiar from the midterm if you answered that particular question correctly. And then on the M step, we'll use those inferred probability distributions over the unobserved S variable to estimate a new vector of parameters for the Bayes net. And here is showing just the example of the parameter that happens to predict the probability that S equals 1, given that its two immediate parents have the values I and j. And the interesting thing here is that we derive this by working through the arithmetic on what it takes to maximize that expected full data log likelihood. But once we finish the arithmetic, we get this expression, which looks remarkably similar to our maximum likelihood estimate that we would have used in the case that we had fully observed data. There we would simply have counted delta here as a little indicator function that's 1 if its arguments are true and 0 otherwise. So this just says we count over all k training examples the number of cases where F, A, and S take on this particular set of values, normalized by the number of cases where F and A take on their values. So this tells us the proportion of times of when this is true, for which this is also true, S equals 1. And here what we have instead is simply the same denominator and almost the same numerator, except that we don't really know whether sk equals 1. All we really know is the probability that it equals 1, the expected value, which for a Boolean variable, which can only be 0 and 1, its expected value is the probability that it equals 1. And so this numerator is just as though we were weighting each example k, the kth example, with, suppose the expected value is 0.7, the probability that s equals 1 is 0.7, then this will turn into a count of 0.7 instead of a count of 1. And when we get to estimating the other parameter about s equaling 0, well, I guess that's 1 minus it, but that would just correspond to this being 0.3 of an example counting toward s equals 0. Yes?
The numerator is only for the unlabeled data, because if you use this formula for all the data, even including the labeled data, it will just like the M step is like the E step, right?
If we use, say that last sentence?
Use the numerator for all the data, including the labeled data.
Yes, yes. Yes, so the point was we use this numerator for all of the data, including the labeled data. And so there we assume that if we have a labeled example where we really can observe the value of s, then we assume if we observe s equals 1, then its expected value is 1, in which case this turns into exactly the same value as this would. Okay. So in fact, in general, it turns out, here's a very nice thing to know. If you have a Bayes net, and all of the random variables are Boolean valued, zeros and one, then you can always write down the EM algorithm by, do I have this on the next? Yes, where all the values are 0 and 1, then you can always write down the M step by going back to your old MLE that you would have used in the case of fully observed data, and just replacing the test that the unobserved value equals 1 by its expected value, regardless of the structure of the base net. That's really nice. It makes it really easy to implement this for arbitrary base net structures. And similarly, if you have a test for whether y equals 0, you replace it by the probability that it's 0, which is 1 minus the probability that it's 1. Okay? Does that make sense? So that's kind of the overview of EM. And now we talked about initially about applying it to this particular base net, FASHM. But we can apply it to any base net. And so right at the end of the class, we kind of rushed through looking at, well, what if we had a naive Bayes classifier? Here's the base net for a naive Bayes classifier, of course. And what if I have this kind of training data, where I have some examples where I observe my x sub i's and also my y, but a couple examples where I don't. Then before we talked about EM, you would have told me, well, we should just train on the first 3 examples and get maximum likelihood estimates. But now we can actually just use EM instead, which allows us to make use of these unlabeled examples too. And in that case, it just turns out this way. When on the E step, of course, what we need to do is for every training example where we don't observe a value, like these two, then we need to estimate its expected value. And that, in this case, that's the expected value of the y variable, the classification, on the kth training example. And we want to estimate the probability that that equals 1, given all the observed values for the kth training example. And that's simply applying our naive Bayes classifier. That's what a naive Bayes classifier does. It gives us the probability distribution over y, given the x sub i's, under the conditional independence assumption. And that probability is the expected value of y sub k. And then on the M step, we just do what we said previously. That is, we go back to our old MLE, which would say, well, if you want to know the probability that x sub I equals j, given that y equals m, you would just count the fraction of times where y equals m, where x sub I also equals j. But now, since we can't really observe whether y equals m for those 2 particular training examples, instead we're going to sum over our training examples the probability that y equals m, instead of testing whether we observe y equals m. And of course, as we said before, in the case where, in those training examples where we do observe y, we just say, well, if we observe y equals m, then we say this probability is 1 for that particular training example. But when we can't observe the example, then we just take this probability, which is exactly what we calculated on the E step. So again, we're taking kind of for each y that we don't observe, if we decide that it's 0.9 probable that it's a 0 and 0.1 probable that it's a 1, then when we're counting up this for y equals 1, we just use 0.1 of an example. It's like we're using a fractional, splitting that example into a partial positive and a partial negative. And again, this just follows directly from going through the full math, starting with the definition of the log likelihood of the full data, the expected log likelihood of the full data, and deriving what would be the formula for theta to maximize that expected log likelihood. Okay. So again, this leads to an incredibly simple algorithm to implement. You could probably take the naive Bayes algorithm that you already have implemented and just modify it to do this very easily, just by taking fractional counts of examples instead of counting the values. So I guess at this point, I have to ask you, you're probably thinking, wait a minute, why on earth would it be the case that unlabeled data would actually tell us anything about how to train this Bayes net? You ought to be asking yourself that. Before you took this course, you certainly would have answered the question, can unlabeled data help us learn to predict the unlabeled variable? You probably would have said no. I hope you would have, if you have common sense. I would have, before I took this course the first time. And so what's going on here? You see what I mean? Isn't this kind of weird that we can take examples for which we don't really know the value of y and still expect to get an improvement in what the accuracy of the classifier that we're learning? So does anybody see a reason why that we might expect that to be the case? Okay, does anybody, yes?
Because we can find some kind of pattern here, like from the previous examples, we know that there is some kind of pattern. So, for example, I know like x is equal to 3 times y. So now if I know the value of x, like I know how x is varying, so I can predict y. I mean, something of that kind.
Right. So that's not a proof, but you're getting informally at the idea that, well, we can use the label data to see things about how the x sub i's do relate to the y's, and that's at least partial information, and so then we ought to be able to use that partial information to squeeze out even more information from these examples. And I agree. And in fact, I guess if I had to boil it down to one sentence, I would say the reason that we might expect these rows in the data set to be useful is if we really do believe that this is the right Bayes net to capture the overall situation. So there's a kind of modeling assumption here that we're using to summarize that data in terms of the parameters of this Bayes net. And if our assumption about this being the right Bayes net is correct, then that summary could actually be useful for helping this. If we pick the wrong Bayes net, then in fact it might be downright damaging to use the negative examples. So again, there is no free lunch. You don't get something for nothing. But if you make, in many cases, we're back to the theme here, that in many cases in machine learning, when we have not as much labeled data as we want, we end up having to make some kind of modeling assumption. And then relying on that plus the data that we do have available, we hope to do better.
Why would it be damaging if you have the wrong one to use unlabeled data?
That's a good point. So why would it be damaging? Now that you asked the question, I wish that what I had said was, you don't expect it to help you on average. But I wonder if anybody can think of an example where it would be damaging. I can't off the top of my head, so I like your point. I'm just thinking that if you have the wrong Bayes net, on average, you wouldn't expect, if your modeling assumptions are wrong, then you wouldn't necessarily expect it to help you to apply them here to infer these values. But I can't say that I can think of an example where it would actually give you a negative impact.
I mean, I can think in the context of a large margin, like for example, I assume provides this large margin, if you make the assumption it has a large margin, you have only two labeled examples, and you pick one with a large margin, but turns out that you don't actually have a large margin.
Yeah.
In other contexts, and supervise them.
That's right. So in other contexts, we can think of examples where making bad assumptions can actually, it can lead you to.
Labeled examples.
Right. So to pick an example that we've talked about, maybe decision trees. If you made an assumption that it's decision trees of depth 2, but actually it was depth 24 that you need, then yeah, I don't think that would actually hurt you. Okay, anyway, Nina is bringing up an example that we haven't gotten to yet in course, so I'm not going to use that example.
Actually, I do have a related question. Do you know in this case how many labeled examples we actually need? Because I would expect this is almost like code training with independent teachers. So there's
Yeah.
very limited data. I think we need like constant number of labeled examples if we have a lot of unlabeled data.
Yeah, so there's also this very interesting question, which we're bringing up, about what volume of data, how many labeled and how many unlabeled examples do we need in order to get this kind of leverage, and how does that look? I think that's kind of, it's related to a technique called co-training. But I don't have a closed formula that tells us how the accuracy goes with that. But I do have an experiment. So let's look at the experiment. So here we're, again, applying exactly this naive Bayes EM algorithm to exactly this kind of data. But the data is taken from 20 news groups, where each article belongs to one of 20 news groups. And the Y variable is a discrete value that takes on 20 possible values. And the X variables are the bag of words in the news group article. And so the classification task is, given a news group article, to predict which news group it came from, which of those 20. And so here, I guess our Y variable is discrete valued. It's not Boolean, but it's 20 valued. And as we saw very briefly, but I wanted to show this again, here's the empirical result that Kamal Nigin came up with when he tried this experiment. And what you see here is the number of labeled examples that he showed the program. What you see here on the bottom is the performance that you get with no unlabeled data. And here you have EM with unlabeled. And this is the accuracy of the classifier evaluated on a separate test set, cross-validated. And so you can see, in fact, in practice, we do get a boost from when we only have 20 labeled examples. That's one example from each of the 20 news groups. Just one labeled example. And in this case, 10,000 unlabeled examples. Then the unlabeled data actually boosts the accuracy significantly over what we would get from that very sparse labeled data. The other trend you see here is that the more labeled data we have, the less the unlabeled data improves the situation. Right? Which kind of makes sense, right? If this curve continued all the way to downtown Pittsburgh, asymptotically, as the amount of labeled data grows to infinity, we wouldn't expect the unlabeled data to be useful at all. Okay, so that's what we see in practice. So despite my own misgivings about why on earth unlabeled data would help us in this situation, and knowing, furthermore, that the naive Bayes conditional independence assumption is just dead wrong when it comes to bag of words classification, despite that, the empirical evidence is that we can get leverage. Okay. So here's another piece of data from the same paper. In this case, instead of using the 20 news groups data, Kamal used the same algorithm, but he applied it to some web pages. And the problem was to classify whether a web page was the home page of a course, of a class, or some other kind of web page. And with this, and again, using the unlabeled data helps. But in this case, this plot shows, oh, and I should tell you, in this case, again, this experiment was done with just one labeled example of a course page, and one labeled example of each of the other classes. I think there were 4 classes here: course page, personal homepage, research project homepage, and university homepage. So what you see here is on the first E step, and the first M step, I'm sorry, just using the labeled data to train the first naive Bayes classifier. Labeled data only, because at that point we don't, well, that's how we began. So that we start on the M step instead of the E step, because to do the E step, you need to have some parameters theta. So we start on the M step. And so just using the label data, here's the rank ordering of different words in the bag of words, the top one being intelligence, that are ranked by the probability of seeing the word, given that it is a course, over the probability of seeing the word given that it's not. So in other words, intelligence is the best indicator, according to the first iteration, about whether a web page is the home page of a course. And the second one, DD, just means 2 digits, like 23 or 47. And then artificial and you can see. So in fact, this home page that was labeled, or sorry, this web page that was labeled as a course page was in fact the AI course page at Dartmouth University. So that kind of explains why these features are here. But then using the same one training labeled example, but the other unlabeled examples, after the first iteration of EM, here was the ranking, and after the second iteration, here was the ranking. And you see that even after just 2 iterations of EM, we have what I think are much more sensible, heavily weighted words for deciding that a document is a course homepage. So all the D's are, again, digits. So there are all kinds of digit things that indicate it might be a course page. And then words like lecture and homework and assignment and handout. So here you can see, in fact, you can get some insight into what's happening with the EM. What's happening, in this case, informally, I would characterize, we started with just one labeled example, the Dartmouth University homepage. But then, given that naive Bayes classifier, which was very overfit to this one training example, once we applied it to all the unlabeled examples, the examples that got characterized as course pages by that not very good naive Bayes classifier had a more reasonable distribution of words in them that separated them from the others. And then that one was used to then further drive the EM process one more step. And so what's happening is information is trickling into these learned conditional probabilities of individual words given the class. But it's getting better and better as we apply it to larger and larger set of data. And so here we have words that aren't so overfit to the single labeled example.
Somehow magically things go in the right direction as opposed to going in the wrong direction.
Yeah, right. So we are going in the right direction. But it happens, if you repeat this, this is not just a cherry-picked experiment. I was around when Kamal was doing this, and this very repeatable kind of phenomena. All right, so here's one final plot that, again, gives some insight into how the performance is influenced by different numbers of labeled and unlabeled examples. So here we see the accuracy. Here we see the number of unlabeled documents. And each curve here corresponds, number of unlabeled. And each curve here corresponds to the number of labeled examples. And so again, we see what intuitively makes sense, that this curve with the triangles is 40 labeled documents, whereas the top curve is 3,000 labeled examples. And so as we might expect, the more labeled examples, the better we do at the beginning, and the less benefit we get from the unlabeled data. But in all cases, the unlabeled data does not hurt us and tends to help to some degree, especially when we don't have very many labeled examples. Another way to think about this, by the way, yeah, question.
Is this graph actually showing the leverage actually influence the accuracy of the algorithm?
Does it show what?
Show how the leverage of label and delabel actually.
Well, I wouldn't say it shows how, but it shows that it helps. And I think that's really all we can conclude from this. But I think another way of thinking about what the unlabeled data provides us, if you think about it, the unlabeled data are samples of the data minus y, right? So we're getting the x's without the y, we're getting the bag of words without the label. So the unlabeled data is really giving us information about the joint distribution over these things. That's really what the unlabeled data is giving us, right? If I have infinite unlabeled data, then I can perfectly estimate what this is, or this kind of unlabeled data. Then I have perfect knowledge of this. And that's all I know in terms of the joint distribution on x sub i's and y's. The unlabeled data is just telling me this part of it. And because the EM process operates on individual examples, information can sneak in about the non-independence of xi and xj. Because remember, we're estimating those y values for each individual document. And even though our model is assuming that these are conditionally independent, the documents themselves might not exhibit that property. And so I think there is another kind of way that the EM process is guided by the actual empirical distribution here, rather than the model assumed distribution. Okay, so there's the story of EM, except the punchline. The punchline is, well, we were just looking at examples where we had only one labeled example, and still we found that the unlabeled data was interesting. What if we go to 0? What if we only have unlabeled data and no labeled data whatsoever? Well, then we have a problem that many people call the clustering problem. Suppose I give you a bunch of documents, maybe they're all the emails we find in your email folder, and we just want to cluster them into similar groups. I don't have labels. I just want to know what are the, let's say, 6 clusters of documents in your email folder. Well, that's just like EM, but where we have none of the documents labeled, right? So this actually is a very viable clustering algorithm. So in general, when I talk about clustering, what I mean is just given a set of unlabeled points, group them into clusters. There are lots of examples of where you'd like to do that. People do it all the time. To turn this into an EM problem, all we have to do is go back to our naive Bayes classifier and just assume, for example, that we have a naive Bayes classifier with 0 y labels. Or more generally, what I'll say is that we assume that the points, the x vectors, x1 through xn, is each training example, unlabeled. What I really end up assuming, including in my naive Bayes classifier, is that my x vectors follow some distribution which I can characterize as a mixture of multiple different distributions. That is, each cluster is really a different distribution in the same sense that in the naive Bayes classifier, each value of a y equals 0, y equals 1, we learn a different distribution of x given the y. And then to classify a new example, of course, we just look, is it more probable that this x observed x vector was generated by the y equals 1 distribution or by the y equals 0 distribution? Right? So that's a mixture distribution in the sense that the real distribution over all of the x vector training examples is a mixture of the y equals 1 distribution plus some other proportion, depending on the priors on y, this second distribution. So in general, I can write a mixture distribution as just in exactly this way. Here I happen to use the variable z instead of y, but it's the same idea. So I can say in clustering, I typically, if I want to be a Bayesian clusterer, then what I do is I say, or use a probabilistic clustering model, what I say is I'm observing these examples of each of which is a vector of n features. And the probability distribution over those examples is a mixture of different distributions for each cluster, each z. Okay. And today I want to talk about the analog of the Gaussian naive Bayes classifier. So in this case, I'll assume that each of my data points is generated by one of my Gaussian distributions. And again, if I had a naive Bayes, Gaussian naive Bayes classifier, I'd learn a Gaussian distribution over the x's for y equals 1, another one for y equals 0, or z equals 1, z equals 0. And so I could say the way that I generate a sample from this mixture distribution is that I randomly choose one of my Gaussians according to the probability that the data would be generated by Gaussian sub I, by the ith cluster. And then I use the Gaussian distribution associated with z equals I. It has its own mean and variance to generate a data point according to that. Okay? So it's just new terminology for the same idea we've had, right? So a typical picture of a mixture distribution could look like this. Here I have just x1 and x2. All these black dots are points. And if you ask me to model that as a mixture of Gaussians, then I might come up with 3 shown here. Okay. I could have used the same picture when we were talking about Gaussian naive Bayes classifiers by just announcing that these points were labeled class 1, these points were labeled class 2, these points were labeled class 3, and then asking what would the trained, supervised trained Gaussian distributions for those 3 classes look like, and we could have used this picture. It's the same situation, it's just that now we don't know any of the labels, so we're going to use EM to calculate them. Okay, so let's do it. So if we want to do an EM algorithm to build a clustering algorithm that assumes my x data points are these vectors of xi through xn, that they're real valued, and therefore a Gaussian distribution is the appropriate way of characterizing them, then actually in this derivation I'm going to make life simple by assuming they are conditionally independent given z, the same assumption that we make for a naive Bayes classifier. And then I'll, furthermore, just to keep things simple, let's assume there are only 2 clusters that I'm looking for. I know in advance that I'm looking for just 2 clusters. So z could be 0 or 1. And then the probability of seeing x is just the sum over z equals 1 and z equals 0 of the product of observing all of the features of that particular X example. And if I'm assuming that this is a Gaussian, then I have a normal distribution which tells me the probability of a particular value given the mean for the jth cluster, and it's sigma. And here I'm making an assumption that we made before when we did Gaussian naive Bayes, that let's just assume the sigmas are the same for all the clusters. We don't have to assume that. But it makes the arithmetic easy. And furthermore, let's assume that sigma is known, that variance, just to make the arithmetic easy. And so then the only thing that I don't know are the class priors for each z. So like, and I'll use pi for that. So pi really means the class prior that z equals I. So I need the priors on all the possible values, all the possible clusters. And then I need the mean for each cluster. And those are the parameters I don't know. Okay, so now we can work through our EM arithmetic on that. Here's EM again. When we work that through, we have to, on the E step, estimate the probability for the cluster label given the nth training example. Since we don't observe its cluster label, we have to get the probability distribution on the nth example's cluster label z. And that's just the usual naive Bayes formula, which once I convert it, that's just Bayes' rule. Once I convert it to naive Bayes, then I can replace the probability of the joint set of x sub i's by their products. There's the naive Bayes step. And so then if I plug in my normal distribution for p of x sub I given z, and this for the prior, then I can express that in terms of the parameters that I'm trying to estimate. So then this can give me, with my current parameters, I can just get all the probabilities for every data point. For the nth data point, I'll calculate the probability that it belongs to the zth cluster in this way. So that's the E step. Effectively, I'm just applying the naive Bayes classifier, Gaussian naive Bayes. And then on the M step, what I'm going to do is I have to maximize, again, the expected joint. I have to maximize this quantity, the expected joint likelihood, which I can factor in this way, right? Chain rule, probability of x and z can be factored into the probability of x given z times the probability of z. And if I factor it that way, then I notice that, say, pi, which is my class prior, remember, pi is just the probability that z z equals 1. I'll just say pi sub I equals the probability that z equals I. So then pi really has no influence on the first thing. Pi is only telling me about the probability of z. And the first term there is x given z, so that's not it. But it only is influenced by the second term. So the only one pi influences is this. And therefore, all I really need to do is maximize, pick the pi that maximizes that second term. Which again, I can write out in a form that should look familiar. This is kind of like our coin flip likelihood, right? Where we have the probability of 1, probability of 0 raised to the exponent, which is the count of times. And so if I work that through, I could see the derivation and then of that expression, and then I can take its derivative with respect to pi, set it to 0, and I end up with this expression for estimating pi for, let's say, z equals 1 instead of 0. It's just this fraction think of the expected value of z is, again, the probability that z equals 1 instead of 0 summed over all my examples, plus the probability that it equals 0 summed over all my examples. And of course, that's going to be just the number of examples. And then the numerator, again, is the probability mass associated over all examples, summed over all examples, the probability mass associated with z equals 1, the expected value of z. So again, this is the expected value version of what would have been just the count, the usual count if we had observed labels. So it all works out, again, very conveniently. And so I have to do the same thing to get my other parameters, which are the means, the mu's associated with each of the x sub i's, right? I need to know, given that z equals 1, what is the Gaussian distribution on x1 and on x2 and on x3? So I need to know, given that z equals value j, what is the mean of the Gaussian distribution on x sub I? And you can work through the arithmetic on that. And again, it turns out to be an expression which is just the one you would have guessed that's a variant of the MLE. That is, again, we're counting in the denominator the probability mass associated with z being 1 summed over all training examples. And in the numerator, we're taking that times xi. So that gives us kind of the mean of x sub I weighted by the probability that the nth example actually belongs in the cluster z. So again, it's just the probabilistic, the expected value of the mean. Okay, so when we do that, we end up with the following very straightforward EM algorithm for completely unlabeled data, clustering. So again, on the E step, we have to calculate the probability or the expected value of the cluster that the nth training example belongs to. And then on the M step, we're going to use those probabilities right here to get the probabilistically weighted means associated with z equals j and x sub i's value and variable x sub I. Okay, so again, very simple algorithm, but it follows from a very fundamental assumption, just that the data was somehow generated by a mixture of Gaussians. We don't know what those Gaussians are, but here's an algorithm for estimating iteratively what the means are for each of those Gaussians. And in this case, I'm assuming the variances are known, but if they're not known, we could also work out a more intricate algorithm that here would have to estimate not just the, here would have to estimate not just the pi's, but also the sigmas. All right, so if you put this all together, there's a beautiful Java applet that illustrates this. And the only problem with the Java applet is that Microsoft Explorer does not trust Java anymore. And so when I tried to run this before, I ran into security warnings, and I couldn't get through to the Java applet. So there are instructions here how you can run that Java applet. And if we have time at the end of the lecture, I brought a second computer, which I've disabused of the idea that there's anything like security. And we can use that second computer and plug it in and look at the applet together. But if not, I encourage you to play with this applet. It's very cool, because what it does is it can generate a random set of points, and then you can step through the EM process looking iteratively at the estimates of the mu's and sigmas, the Gaussians associated with the different clusters. And you can get a feeling, just like we looked in Kummel's data when he was applying EM to learning the naive Bayes classifier for those course web pages, we could see what was going on. This applet's a beautiful way of looking at the iterative estimation of this Gaussian. So I encourage you to look at this. And if we have time, I'll pull up my other computer. Okay, so that's what I want to say about EM. It really is a very powerful idea. And to me, one of the more surprising things to come out of machine learning, the idea that you can actually get value from unlabeled data if you make appropriate modeling assumptions, is quite remarkable. And EM is the most general technique that I'm aware of for squeezing information out of unlabeled data. Basically, if you have a Bayes net, you can derive an EM algorithm. So you should know these things, but I think there's no need to go through the list. You can see them, and I think you know what they mean. Yep?
So I guess, I'm sure that one can prove it in the worst case, this could take exponential number of steps to converge. Right? I know that's true for k-means, under some assumption you can recover k-means through this thinking, and I know for sure that for k-means in the worst case it can take exponential.
Can take exponential.
Even in 2 dimensions.
So Nina's bringing up, what's the computational complexity of EM? How long does it take to converge? In the worst case, it probably is very bad.
And the question would be how about typical cases?
In practice, in typical cases, EM converges very quickly. Like, for example, compared to gradient descent, you've implemented some gradient descent algorithm, I think, where it might have taken you hundreds of steps to converge. It's actually very rare that EM would take even 100 steps. In these kind of clustering problems that you see, it's usually like dozens of steps. So in practice, it can be very tractable. It's not as fast, of course, as getting a maximum likelihood estimate from fully observed data. That corresponds to half of a single EM iteration, right? Like the E step, or sorry, the first M step. If you have fully observed data, you could think of the standard MLE as just doing half of the first EM step and then being done. So it is slower than that because you have to iteratively do this and keep doing those MLE-like estimates on the M steps. Yes?
What happens if you want to find a global optimum? Are there any nice ways to do it?
Yeah. What if you want to find a global optimum? The problem with EM is that it's, if you have an objective function you're trying to optimize, which in general is the expected log likelihood, if that objective happens to be non-convex, the best you can guarantee is that you'll find a local optimum there. If you really want to find the global optimum, some Bayes nets, if you design the right Bayes net, will have a convex likelihood function, so you might be lucky. But if you're not lucky, which in the random case, you will not be lucky if you choose a random Bayes net, then there are kind of engineering tricks like starting EM, running EM multiple times with different starting, random starting choices for the parameters. And I don't really know of a better technique than that. There could be one, but does anybody know of a better technique than random restart to get global optimum for EM? Yeah, I fear that's kind of the general situation.
Design a different algorithm.
What?
Design a different algorithm.
Design a different algorithm, that's right, with a convex objective. And there are many other clustering algorithms. We're not going to spend a lot of time in this course on clustering, but you should be aware that EM is not the only clustering algorithm. But it is the natural one you get if you take a probabilistic viewpoint on how the data was generated. If you say it's generated by a mixture distribution, Gaussian mixture, or even a mixture of Bernoulli-style discrete valued variables, you'll get an EM algorithm as the natural solution. Okay, so before we leave Bayes nets, which we are going to do temporarily at least at the end of today's lecture, before we leave them behind, I owe you to come back to this question of how are you going to train a Bayes net if you don't know the structure in advance. Several people have asked that question during class and after in office hours. And in general, this is a somewhat more difficult problem, especially if you don't have fully observed data to learn the structure from. Then it gets really harder. But let's take a look at the case where we do have fully observed data, but we don't know what the Bayes net structure is. Then what would you do there? And it turns out there is a pretty interesting set of results on this. My favorite result is the one we'll cover here, which is the Chow-Liu algorithm. And here's the idea. Suppose that I'm willing to restrict myself to a Bayes net graph which forms a tree. So of course, that's a restrictive assumption. There are Bayes nets that don't form trees. But if I'm willing to assume that I'm only going to search around in graphs that happen to be trees, then there's actually a very nice algorithm for finding the best Bayes net structure for a particular definition of best. So suppose X is my vector of random variables in the Bayes net, X1, X2, Xn.
Just to clarify, this is a polynomial time algorithm, right?
Pardon me?
This is a polynomial time algorithm. And in general, you can do exhaustive search, but this is a polynomial time algorithm in this case.
This is an n squared algorithm, in fact. Suppose T of X is the tree-structured network, the distribution defined by a tree-structured network. But P of X is the true distribution on my set of random variables. Okay, so just to set this up. So I have a set of random variables, x1 through xn. I don't know the graph for the Bayes net. Suppose the true distribution is P of X, and I have a tree-structured network, and the parameters estimated for that. And so my tree-structured network has probability distribution, I'll call it T of X, as opposed to the true distribution, P of X. Then the Chow-Liu algorithm minimizes what's called the Kullback-Leibler divergence. Many of us call it KL divergence, if we don't like so many syllables. And the KL divergence is actually a measure of how different two distributions are, two probability distributions. And it's a very simple definition. So given two probability distributions, P and T, over the same set of random variables, the KL divergence is just the expected value under P of X of the log odds ratio of the probability that would be assigned for by P and the probability that would be assigned by T. Okay. So what to notice about this definition? Suppose P equals T, then this ratio will be 1. The log of 1 will be 0. And so the KL divergence equals 0. That's good. The more different P and T are, then the further from 0 this is going to get to be. Also, the other thing to notice here is that the KL divergence of P and T is not the same as the KL divergence of T and P. This is asymmetric, because we're taking the expected value under the first distribution of the ratio of the two. And so if instead I wrote my T here and my P here, then I'd have the expected value under T. So it's not a symmetric, it's not really a distance metric, but it's called the KL divergence.
So just a comment, I mean, of course you can minimize this in general, right? And you could try to find, sorry to over that, you could try in general, even if it doesn't have to be a tree structure, right?
Oh, right. Yeah, this is a general definition about divergence or divergence between any two probability distributions.
Without assuming that the basenet you are finding is a tree, you could try to minimize this. It's just computationally intractable. So that's why the algorithm is specialized to trees.
Right, 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 good. So the point Nina is making is right on target that, of course, in general, even if it wasn't a tree distribution, this would be a good measure for minimizing the distribution that we get out of our learned graph structure and the true distribution. This is the thing we'd want, a very nice thing to minimize. And why are we talking about tree networks? Simply because, in general, the problem of learning networks is intractable. But it turns out if we restrict ourselves to tree-structured networks, then we get a very tractable algorithm, where if n is the number of random variables, then we'll see this is an n-squared algorithm in terms of computation time. All right? So there's the goal. The goal is clear, right? We're trying to learn a basenet structure which will be very similar to the true distribution, which will, and when I say be very similar, I mean once we learn the parameters, the optimal parameters associated with that tree structure, then we'll have a probability distribution very similar to the true one. Okay, so let's see how that works. Here's the key result. The key result is that if you want to minimize that KL divergence between two distributions P and T, it's sufficient to find the tree network that maximizes the sum of the mutual information across all edges in that tree. Remember mutual information? Remember lecture 1? Decision trees. Mutual information was our statistic that we used to choose the next edge, the next attribute that we're going to test in the tree, the decision tree, as we were growing it top down. So here we have our friend mutual information back again, but this time a different way. Just to remind you, the mutual information between two random variables A and B is just this quantity. The sum over all of their possible respective values of their joint probability times the log of this fraction. And you can think of this fraction, by the way, as how bad an approximation of the joint distribution would it be if we assumed they were independent. Right? If these are independent, then this will equal this, and this will be a 1, and the log will be 0, and there's no mutual information. They're independent. But if they're not independent, then these will be different, and that'll be a non-zero quantity, and the more different they are, the more of a non-zero quantity it'll be. Okay, so mutual information, our old friend, is back, and it's because if you have a tree network with n nodes in it, then you can prove, I'm not proving it here, but you can, that the KL divergence between the true distribution and the distribution that that tree network will represent, which is just defined again, this is the generic definition of KL divergence. In the case of a tree structure, it happens to be equal to this quantity, which is what? This quantity is the sum over I being the index for the nodes, so the sum over nodes of the mutual information between that node and its parents, its immediate parents in the basenet, plus the sum over nodes of their entropy, H is our entropy, again, lecture 1, minus the joint entropy over the joint distribution. Okay, so this happens to be true, that the KL divergence can be expressed in terms of the sum over every variable of its mutual information with respect to its immediate parents, plus some entropy terms. Now, interestingly, if we're trying to design a tree and choose the edges between these variables, then the only one of these three terms that that's going to influence is what? Well, it's not going to influence this, because the entropy of this set of random variables is what it is, has nothing to do with my tree. So adjusting the tree won't change this quantity. Adjusting the tree won't change the entropy of individual variables. That's just whatever it is. The only thing I can adjust with my tree is the assignment of immediate parents. And of course, being a tree, you have just one immediate parent. That's what it means to be a tree. So the only thing that I can, if I'm trying to maximize this, minimize, I want the smallest KL divergence. If I'm trying to minimize this expression, which is then the only term that I have to worry about is this term. And minimizing this term is the same as maximizing if I leave out the minus sign. So I want to maximize the sum of the mutual informations over all my variables. So that's the tree I want to pick. I want the one that maximizes that. How can we do that? Well, here's the algorithm. So for each pair of variables, so I have x1 through xn, for a pair like A and B, first I'll use all my training data. I'm trying to learn the graph structure. I'm going to use all my training data to estimate the joint probability, P of A, B, and their marginal probabilities, P of A and P of B. So if A is a Boolean variable and I want P of A, I just count how many times it's true over how many data entries I have. And then, using those things, for each pair of variables, I can compute its mutual information. And so now I have a matrix of all my variables against all my variables, and the ijth entry tells me the mutual information between variable I and variable j. Okay, that's an n-squared operation because they're n-squared pairs. Now what I'm going to do is I'm going to calculate the maximum spanning tree over this set of variables using edge weights, which are the mutual informations I just computed. And it turns out this is also an n-squared operation, finding the maximum spanning tree. And then once I find that, I just put arrows on my edges to make it a tree, a directed acyclic graph. And then now I've got the structure, now I can go ahead and learn the conditional probability distributions associated with each node in my graph. Okay. So that's the algorithm. Let's look at what happens if we have a particular example. So here's a situation where we have random variables A through G. And let's say that the edges here are all of the are many of the pairwise mutual information edges. If I want now to find the maximum spanning tree, all I have to do is start by, it's a greedy algorithm. I find the edge that has the largest weight, in this case 1/5. So I'll choose that edge to be part of my tree. I've made it green. And now, given that, I want to find the next best edge, which I guess here's another 1/5. So I'll add that to my tree. What's the next best? I see a 1/6 here. So I'll add that one. And now I see a 1/7 up there. So I can add that one. Oh, but now that I add that one, given that I have those two green edges, B and D I don't have to worry about B and D. In fact, I wouldn't want to add an edge between B and D because it would be a non-tree. So I'll color that one red, meaning ignore it from here on. Okay, and then I just iterate on that. My next best edge is, I guess, B to E, which now means that the B to C edge should be removed from consideration. I can't add that. And so do the E to F and D ones. Those should be removed. So now I only have two more left to consider. And of those two, I guess EG is the better. Okay? So that's the maximum spanning tree algorithm in a nutshell. And if I start with a graph with all the mutual informations pairwise on it, here in green is my learned tree structure. That's the best tree structure you can find if your definition of best is the minimum KL divergence between the joint distribution represented by this and the joint distribution that actually generated my training data. Yes?
In the initial case, why have we not taken the information gain between D and C?
Yeah, we really should have them all in there. It just would be too messy a graph to put on the slide. So for this, I left out some of the edges. But in general, we should have the fully connected graph. It's just messy.
The algorithm that you run is classical algorithm for finding a maximum spanning tree, but you can apply any algorithm for finding maximum spanning tree. You can apply prime or any other algorithms. You want to use this classical,
Right.
like single linkage of classical.
So that you're saying there are many algorithms for doing this.
Yeah.
Right.
Prime and Borovka.
Right, but n squared is a good, is the complexity of this. Notice just to compute the mutual informations pairwise, that's an n squared operation to begin with. So, and this algorithm is obviously n squared also. You can do better in terms of the spanning tree. Okay, so there are better complexity spanning tree algorithms, but the overall algorithm, because you have to compute all the pairwise mutual informations, is still n squared. Yep.
And would this always reach the global maximum case, or it would fall into a local maximum?
No, this is guaranteed to be the lowest KL divergence tree network that you can find. So there's no local maximum problem here. Of course, your network might not actually be a tree, but the one that generated the data might not have been a tree. But if you're looking for a tree, then you can use it this way.
That's kind of nice because it's agnostic, right? You don't have to assume that the true underlying probability distribution is actually a tree. It's agnostic.
Right, it's just getting the best fit to whatever the underlying distribution is. But
When you can do agnostic efficiently.
that's right. Yes?
How do you decide which node is a parent node?
Which node is what?
Parent node.
Oh, it doesn't matter. So this is weird, isn't it? As long as you label this as a tree somehow, you will get the right answer. So I could make this the root of the tree and assign arrows going out like that. Or I could make this the root of the tree and the arrows would go this way. And remember how we pointed out that if I took the chain rule to factor the joint distribution over a set of variables, that I could apply that chain rule several different ways to get different ways of factoring equally good ways, in fact, identical ways. They're different factorizations, but their product represents the same joint distribution. The same is true here. Once you have this, you can put the arrows in any direction that makes it a tree. And if you do it one way and I do it another way, it will turn out to be the case that there is no set of parameters I can learn that define a joint distribution that you won't also be able to learn by choosing parameters for your tree.
Yeah, I don't think the factorization would be the same for any direction of arrows, because let's say you have one node that leads to 10 nodes. That's like naive Bayes. But if I flip it around, that's a completely different factorization. That's much more difficult to learn. Like if I just have one node that goes out to 10 nodes, that's naive Bayes. But if I flip it around, like I have 10 nodes going to a single node, that seems completely different.
Oh, I see. You're saying, let me do this on a blank slide. You're saying if I have this tree
Where everything is going out.
and I go this way, it looks very non-naive Bayesy. Whereas if I do it the other way,
So it would be significantly, like it doesn't seem like they're the same. They're not the same factorization.
they're not the same factorization, that's for sure. The question is whether they represent the same distribution. Colliders, deseparation. There's another one, right? If I just move this guy around, put him up to the top, did I get this? So there are a number of these. Okay, this is not a shower problem. You need a piece of paper. Next class, tell me the answer to this question. It's a really good question. It's not obvious to me. You're pointing out that for the same unlabeled graph, I can put edges, say, all three of these ways, for example. And two of them don't look like naive Bayes, and one does. The question is whether they capture the same set of independence assumptions. And I don't know offhand. So figure that out. Extra credit to anybody who comes in with the proof of the answer to that. Yes?
Can I have a try?
Yeah.
So yeah, actually here, for the learning of the net structure,
Uh-huh.
what do we care about is, the network can represent
Uh-huh.
data, right?
All we care about is the network of dependencies.
Can represent our data.
How will it fit the data?
Oh, can it represent the data?
Yeah, and also all these, they
That's
are
pretty
using the
good.
same, they are not the same factorization.
Yeah,
But if they can represent the data,
just as well. I see. So this is a very astute point. The point is, what's your name? Ing. Says, notice that what we're trying to optimize here in this algorithm is to minimize the KL divergence between the empirical distribution represented by our data and this tree. And so it may be that, so the only property we care about here, or that we're guaranteeing, is that these three distinct graph structures equally well minimize that KL divergence. We're not necessarily guaranteeing that they make the same set of conditional independence assumptions, only that they have the same KL divergence to the true distribution. That's a really good point. So that's the thing we actually want to prove. But it would still be interesting to see whether different conditional independence, they do look mighty different, I have to say. But then there is this collider thing going on, which makes it a little tricky to think quickly about it. Yes?
Does it being a tree mean that it can only have one parent node?
Yeah.
So in that case, the one on the left wouldn't even be possible because essentially we've got three parent nodes for the one.
Oh, thank you. Thank you. This is not a tree.
And then I guess either the second or the third would be possible, but it's a question of a root node, and I think whether it's a root node. So I think that the algorithm we talked about would only allow one possibility. Like here, I mean.
The algorithm that we talked about would give us some kind of structure like this, let's say. And then one possibility would be to label the edges this way, and the other would be to label them this way. Which is this one.
All right, so those two both work.
So those two don't. But your point is very good, that the top left one that was an illegal move. But yeah, these are different looking. Those top two ones are. Good, I like this question. Thank you for bringing that up. So let's stop there. Well, let me make one quick comment. One of the interesting projects that people have explored in the past, remember your project, the idea is to propose something where at the midway point in the project, you will have something to show as an implemented experiment set of results. And then on part 2 of the project, you do something more ambitious. So one project that people have done in the past that has turned out kind of interesting was to implement a naive Bayes classifier for some data set initially in part 1. And then in part 2, explore structure learning, BayesNet structure learning algorithms to try to learn better Bayes nets than the naive Bayes one. And one particularly interesting idea, due to Nir Friedman, is to take this Chow-Liu algorithm, which can learn a set of random variables, or a tree over a set of random variables. And Nir did the following thing. He said, what if I start with a naive Bayes structure, and then I just ask my algorithm to learn the dependencies among these x sub i's. And I'll, in fact, use the Chow-Liu algorithm to learn a tree-structured network of dependencies among these variables. And so that's a very tractable way of partially easing off from the naive Bayes assumption that these are all conditionally independent of y, by allowing yourself to put some edges between here in the form of a tree.